So let's start with kind of a simple example to get a picture for what's going on. So I've got a matrix A here, and I'm given a U and V, and I want to find AU and AV. So let's start with AU. So if I find AU and multiply, what do we get on the back end? What's our product? -5, -1. Okay. Thank you, Felix and Gerline. And what I want to point out is that these two vectors here are not scalar multiples of each other. And that might make you predict what's going to happen on the next one. Whew, you guys are so smart. So if we look at AV, it'll be the same UA, 3, -2, 1, 0, multiply by -1, 1. And what do you get here? I've got some fortuitous from Gerline. Thank you. Sorry, not by the same thing. Huh? Me smart. Me teach college. If you multiply by the same thing, you better get the same result out. Let me try that again. Multiply by 2, 1. And like Gerline said, if you do this right, you'll get out 4, 2. And so what do you notice about the relationship between the green vector, or between the two green vectors? Yeah, specifically the output is double the input, or they're scalar multiples, right? So maybe we could say, hey, this thing is equal to 2 times 2, 1. Okay. So because they're scalar multiples, that means we're going to have an eigenvector and an eigenvalue. And so we would say that this number 2 is our eigenvalue. And then we would say that our eigenvector graphically, what's happening is when we use the yellow vector, we started in the direction U, and then after the linear transformation, we ended up in the direction of AU, and those are not parallel to each other. But in the case of the green vector, we started here with V, and we ended with AV, which was parallel. So focusing in on this, let's get ourselves a little bit more vocabulary and notation. So let's get this definition. So an eigenvector of an n by n matrix A is a non-zero vector x such that ax equals lambda x for some scalar lambda. A scalar lambda is called an eigenvalue of A if there's a non-trivial solution x of ax equals lambda x, such that x is called an eigenvector corresponding to lambda. Just briefly, there's one x that will never be an eigenvector. What's the x that will never be an eigenvector? From Dibs and Ben and Kevin, 0. Yep. So you'll never have 0 as an eigenvector. You can have 0 as an eigenvalue. questions? Okay, so in this particular case up above, we're saying that we had AV equal to lambda V, and the lambda in this case was our eigenvalue of 2, and the V, our eigenvector, was that one right there. Okay. So let's kind of play with this a second time in example 2 and see how it all plays out. So first, is 3, 2 an eigenvector of this matrix? We could answer this a bunch of ways, but kind of the straightforward way is just to multiply and see what happens. So we could take 10, -9, 4, -2, and multiply by 3, 2. What's the product equal to? From Gerline, I've got 12, 8. And so we're looking at the 3, 2 and the 12, 8. Are these scalar multiples of each other? Yeah. So this would be like 4 times 3, 2. And so here we're saying that our lambda is 4, and our eigenvector is V. Yep, thanks, Alex, Gerald, Gerline, Twee, Ben, Adis, Sammy. Take a guess. Is the next one gonna work? Whoa! Probably not. So we try again. 10, -9, 4, -2, times 3, 2. What you gonna get out this time? Got an 11, 6. And so notice what you're looking at is the relationship. You're saying, here's the relationship between 2 and 6. So 2 times 3 is 6, but 3 times 3 is not 11. So in this case, we have that it's not an eigenvector. Did I do it? Oh my gosh. You guys must be having it. Got it? Now does our math actually work? I'm like making up math today. I must be so excited about my friends liking me that I lost the ability to write things properly. So yeah, if only dibs. But it actually doesn't get, this section stays okay. All right. So notice that in example 1 and example 2, what we've done is I've given you vectors and I've said, let's verify things. So you haven't had to actually find the vectors. So in this next example, we're going to find the vector starting with the eigenvalue. So here, I want to show that 5 is an eigenvalue of the matrix 1, 2, 4, 3, and find the corresponding eigenvector. It's kind of a twofer. So remember, in order to be an eigenvalue, this means we should be able to solve AX equal to 5 times X. And so here's that 5, which is our lambda. And what we're trying to figure out is, are there non-trivial solutions to this equation? So are there x's other than 0 that would make this true? Ahmed asked, are all the eigenvectors of a matrix multiples of each other? That's a good question. Why don't you hold on to that question for a little bit? I think we'll answer it shortly. So here we want to solve ax equals 5x. We're looking for non-trivial solutions. That reminds us of the homogeneous equation. And so we got to kind of bring that homogeneous equation into focus. So we've got ax minus 5x equals 0. And so we're looking for non-trivial solutions to the homogeneous equation. And then you probably see an x in common. And so you might think to yourself, hey, I see an x in common, let me factor. Right? And so you go to factor and something weird happens. Okay. I want to point something out. What's wrong with this blue statement right there? Yeah, from Felix, that the A is a matrix and 5 is probably a number. And so how the heck do you subtract 5 from a matrix? That doesn't even make sense. So we need to have this is a matrix and a scalar. And so we need to have a matrix minus a matrix. And so we're going to play a pretty clever little game. Come on. So rather than just subtracting 5, I'm going to subtract 5i. Okay. So if you think about it, this would be like saying that instead of having a 5 up here, or 5x, it's like having a 5ix, which sort of looks like 6 with my handwriting. But anyway, and this will always work. So you can always multiply by an I, because it's the identity matrix, it doesn't change anything. So we now have a minus 5i times x equals 0. This is the homogeneous equation. We're looking for non-trivial solutions. So effectively, what we're looking for is the null space of a minus 5i. The null space of a minus 5i. So do you remember how we find the null space? How do we find the null space, or the non-trivial solutions, if you will? So we got to ref it. So we need to ref a minus 5i augmented with 0. Right? And so this would be the same thing as trying to ref. So notice what we're doing is we're going to subtract. Well, think about what 5i is for a second. Let me just do some scratch. This would be 5005. And so notice when we do the subtraction, what we're going to be doing is we're going to row reduce. We're going to take 5 away, the yellow 5, same 5 as before, 5 away from all of the diagonal entries in A. So A was 1, 2, 4, 3. So now we're going to have, what is that? Negative 4, 2, 4, negative 2, 0, 0. Richard asked, do non-square matrices have eigenvalues and eigenvectors? No, this only applies to square matrices. So notice that the two rows are just scalar multiples of each other. So you can see that you're going to end up with a row of zeros. And so you could row reduce and end up with like 1, negative a half, 0, 0, 0, 0. So again, we're looking for the null space. So if we want to find our null space, this tells us that our x's are equal to x2, our free variable, times what vector? Yeah, from Abed, a half, comma, 1. Okay, yeah, thanks. Gerald and Abe, and then Twee, remember that you have to add the 1/2 to the other side in order to make it work. So tell me what numbers is it okay for x2 to be? That's not a very good sentence. X2 could be, in general, any number that's out there, any real number. Okay, but in this context, we're talking about eigenvectors, and so we're saying that any vector of this form, x equals x2 times 1/2 1, is an eigenvector, except for the one when x2 equals what? There's like one bad x2 value. Yeah, x2 can't be 0 because we're only looking for non-trivial solutions. Okay. So this tells us that thus the eigenvector corresponding to lambda equals 5 is 1/2 1, or maybe if we don't like fractions, we could just multiply this thing by 2. So maybe we just say like 1, 2 is a nicer form of the same thing. So you might say, how do we do this? The first part said, show that it's an eigenvalue of the matrix. We did that by showing that there are non-trivial solutions. Okay, and then the second part said, find a corresponding eigenvector, and we've done that here. So from Gerald and from Dibbs, so we can have infinite eigenvectors. How can we multiply by 2 at the end? Won't that mean that the lambda will change? Nope. The lambda is the same for all of these. What that's saying is that if you started with 1/2 1, then remember your lambda is 5. So if you started with 1/2 1, your output would be 5/2 5. If you started with 1 2, your output would be 5/10. If you started with -3 -6, your output would be -15 -30. Each case, it's any vector that's on this line would be, except for 0, would be an eigenvector, and they would all have the same eigenvalue. So there's an infinite number of eigenvectors, but notice these are all linearly dependent. So there's only one linearly independent vector here, even if there's an infinite number of vectors. Did that answer your question, Gerald? Dibbs? Questions? So the eigenvector must be non-zero. But an eigen can be 0. An eigenvalue of an n by n, sorry, so lambda is an eigenvalue of an n by n matrix if and only if a minus lambda I times x equals 0. This is an important formula. Yeah. Let's see. So notice this is a homogeneous equation. So another name for the solutions to this equation would be the solutions are the null space of A minus lambda I. But we already know that any null space is already a subspace. So this is actually kind of cool. So since we're looking for a null space, we already know that the null space is a subspace of Rn. And so rather than saying we're looking for the null space of A minus lambda I, which is a whole bunch of words, let's see if we can simplify this and say that we're just simply looking for the eigenspace of A. So, like, what is that eigenspace? It's basically all the eigenvectors. And it's a subspace. What vector is never an eigenvector? Yeah, 0. So it's all the eigenvectors plus the 0 vector. So your eigenspace is all the eigenvectors, and then we're going to allow 0 to be in there so that it can be a subspace. And the word eigenspace is nice. We like it simply because it saves us a little bit of writing. Not to mention, it sounds German, so that's cool. So let's find a basis for the eigenspace of the matrix A given and with lambda equals 3. Similar thing to before. So we're going to start with that homogeneous equation. So I need to start with, by solving, A minus 3i times x equals 0. Here's the eigenvalue that was given. We haven't, in the next section, we learn how to find the eigenvalues. In this section, we're just using them. So A minus 3i times x equals 0. So that means we got to row reduce. And remember, the matrix we need to row reduce is the original A matrix, but we're going to subtract 3 from every diagonal entry. So subtract 3 from every diagonal entry. So you'll have 1, 2, 3, -1, -2, -3, 2, 4, 6. Okay. Oh, augmented with 0. Okay. Give me a thumbs up or a question if you related to this matrix. This isn't hard, but it's an important one, so I want to just pause here. So do you understand where that matrix came from? Any questions? Anyone want to pause? second explanation. Again, my diagonal was 419, and I'm going to subtract 3 from every entry in that diagonal. 4 minus 3 is the 1. 1 minus 3, that's negative 2. 9 minus 3, that's the 6. Okay. So good news about this matrix. You probably could see it already. The second row is negative 1 times the first row. The third row is double the first row. So you don't even need a Texan friend to row reduce this one. When you row reduce, you're just going to get 1, 2, 3, 0, 0, 0, 0, 0, 0, 0, 0, 0. Something like that. So this tells us that we would have x's which would be equal to x2 times something plus x3 times something, because x2 and x3 are our free variables. So what's the vector that we multiply x2 by? God, thank you. So I've got negative 2, 1, and 0. And then x3 would be multiplied by negative 3, 0, and 1. Okay. Thanks. Lots of you chimed in. I can still see Ben, Alex, Ryan, Evan, Mahi, Megumi, and Hui in the chat. So what does this do? This tells us that our eigenspace associated with lambda equals 3 is equal to the span of these two vectors. Okay. So that's our eigenspace. Is every vector in this span an eigenvector? Is every vector in this eigenspace an eigenvector? Yeah. All of them are eigenvectors except for 0. And Evan, you must be a programmer because you got your little exclamation mark for the not. So that's nice. I was told that you say that with bang as bangs. You'd say bang 0 is how you'd actually say it. Do they still teach that, or did I make that up? Like, to this day, when I'm using an exclamation mark to mean not, I'm like bang this, because it just sounds so cool. So somebody, you guys can research it. So this is our eigenspace. That's the whole space, and so we might ask for a basis. For the eigenspace would be just the two vectors. Oh, man, maybe I made it up in one of my, maybe my teacher was messing with me. Like, it's totally possible. Like, the teacher's like, oh, wouldn't this be funny? Like, for, who knows? So. All right, so here's my basis right here. Just trying to make sure that you're tracking. What's the difference between the basis and the space itself? Oh. Yes, the space has 0, but what I was pushing for, Anthony and Twee and I think Felix got, is that the basis is just 2 vectors, whereas the eigenspace is a whole subspace. It's got an infinite number of vectors in it. Thanks, Ahmed, for at least making me feel good and telling me that Bang is a real name, that I didn't completely make that up. So, cool. All right, so let's add one little bit to this. So we say that the basis for the eigenspace is here, and so we would say that lambda equals 3 is an eigenvalue with geometric multiplicity of 2. So the new term here is, that looks terrible. Geometric multiplicity, and the 2 is because there are 1, 2 linearly independent eigenvectors. Questions? Okay, let's hit most of what's left. We're not going to hit the proof, but we can hit a couple other things. This theorem 1, this is your friend. Okay, so it says if you have a triangular matrix, that's one where there's zeros above the below the diagonal or zeros above the diagonal, then the eigenvalues are just the entries of along the diagonal. So in this case, we would say that our eigenvalues would be 0, 2, and 3. In this case, I've listed them in increasing order. Sometimes you might list them in decreasing order. So easy to find eigenvalues of diagonal matrices. What does it mean for a matrix to have an eigenvalue of 0? So if you think about that, that's saying that AX equals 0 times X has non-trivial solutions. Okay. So it's like the null space is interesting of the original matrix A. So what I'm saying there is that every square matrix that we've seen already, we've seen square matrices in the past that had 0 as a, or that had non-trivial solutions. Sorry, that had an interesting null space. So in all those cases, 0 was going to be an eigenvalue. We just didn't know anything about eigenvalues at that time. So we've actually already done examples where you've had the eigenvalue of 0. So this means that 0 is an eigenvalue of A if and only if A is not invertible. And we can just add this to our long list. So remember all R things that you had to write down for your assessment, and then I asked you guys about the determinant. So that should be there. So we can just add this to our invertible matrix theorem.
Do we keep on adding to that list as we go on during the class?
I think I say we'll do it. We'll actually add it in the notes in the next section.
Oh,
So you could if you wanted, but I think you're okay. So when we pick this up again, we'll work through this one proof, but I just want to highlight something in the proof. So it basically says that if you have R vectors and you have R eigenvalues, and they're distinct, so as in the eigenvalues aren't the same, then the set of eigenvectors is going to be linearly independent. So you're going to get like this bit of linear independence as the output. So we'll work through the proof of this later, and you'll see how this is helpful to us down the road. But I just wanted to highlight like what the theorem is saying today before we go on. So to prove theorem 2, we're going to prove by contradiction, and we're going to take this whole claim that v1 to vr are eigenvectors with corresponding distinct eigenvalues lambda 1 to lambda r, but we're going to assume that v1 to vr are linearly dependent and then show that we get a contradiction. So let me write that down. So let some n by n matrix A with distinct or with eigenvectors vectors v1 to vr with distinct eigenvalues lambda 1 to lambda r be given. Okay. So there's my let something be given. And so now we are going to suppose that these vectors are linearly dependent. And so just looking ahead, this is a proof by contradiction. So we're trying to show that it's linearly independent. We're going to suppose that it's linearly dependent. We're going to get a contradiction. What do you think that contradiction is going to look like? We'll get to your question in a second, Tibbs. So what do you think this, so there's going to be a contradiction somewhere along the line. What's going to be the contradiction? Yeah, so we could get something, so it's going to show, the contradiction is going to, oh my gosh, the contradiction is going to show us that the vectors are linearly independent. But the contradiction is actually going to be to this statement here that we're going to have distinct eigenvalues. And so what we'll show is that there's no way to have distinct eigenvalues and have those be linearly dependent. So at the end of the day, we're going to show that all the lambdas have to be different than each other. Okay. So if these vectors are, oh, sorry, and let me go back to a question. Dibs asked, how do I know when to use proof by contradiction or some other style? You don't necessarily know on the front end. You try some things and you see which one works. But oftentimes when the claim is that something is unique, then you're going to use some sort of a contradiction type of proof. So it's not a great answer, but at least it's a partial answer. So we're going to suppose that V1 to VR are linearly dependent. So that means that there are non-trivial solutions to the homogeneous equation. But it also, that would be one way of looking at it. But another way of looking at it is that there are some linearly independent vectors on the front end, and then at some point there's a linearly dependent vector. So let's just kind of have an aside. Like, so suppose VP plus 1 is a linear combination of V1 to VP. Okay. So kind of with that in mind, this implies there exists, backwards E, there exists a VP plus 1. That's that green V plus 1 I was talking about. That's equal to C1 V1 plus dot 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 plus CP VP. Okay. So remember, this V plus V P plus 1 is that green vector that can be made from previous vectors. You might be noticing the fact that you have an R here and you have a P here, so, and a P plus 1. So what I'm saying is that there is some vector. In this case, P and P plus 1 must be less than R. I'm just saying one of them has to be a combination of the others. So there exists this V that's a linear combination of all these other, there exists a VP plus 1, there's a combination of all the other V's, and this would be true with not all the C's equal to 0. Okay. And we have V1 to VP are linearly independent. Okay. So I don't have my Legos. I don't have my Legos anymore. Maybe think about it. You think about it this way. Rather than thinking about linear independence, think about it like color on a like pen color or something like that. And so we're, I can't hold all these pens. It's too many. My hands. So I've got all these pens. Each of these represent vectors, and linearly dependent in this context represents a repeated color. So is this one your left? Is this left for you? Okay. So we could ask ourselves, when is the first time in this set that we get a repeated color? Well, you're okay. So in this case, R would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So my R would be 11 because there's 11 pens. Okay. And so then we could ask, when is the first time we get a repeated color? So the first repeated color we get is, actually it looks like it happens right away. It's this second purple pen. Can you see that? So what I'm saying is that my P in this case would be 2, because these ones are linearly independent, e.g. different colors, and P plus 1 would be, in this case, 3, this purple pen, because it's the first repeated color. And so I'm saying that, oh, if I just focus in on these 3 pens, I can ignore all the other ones. The third one is a linear combination of the first 2. And specifically, it's 1 of these and 0 of these. Gives me this one. Make sense? I could try to write all that down, but I don't know which pen to write it with, so I'll just have to say it. Okay, so we have these V's. Let's see what happens. What kind of vectors are these V's? This is our new word, our new German word. So what kind of vectors are these? From Megumi and Felix and Gerline and Twee and Ryan and Richard, these are all eigenvectors. So as soon as they're eigenvectors, you know you got to take advantage of that somewhere along the line. So we're going to left multiply with our A. So this implies that we could take A times VP plus 1, and this would be equal to A times C1 V1 plus plus C PVP. Come back to what? Come back to me. Okay. So let's see what we get on the left. Okay. So remember, every one of these vectors is an eigenvector. So A times V1, A times VP plus 1 would be lambda P plus 1 times VP plus 1. And this will be equal to, you're going to have A times CV1. The C1 can come out. So you're going to have lambda. Let me see if I can try to keep my order the same as in my notes. I would have C1 lambda 1 V1 plus, I think what I really want is it to be CP lambda P VP. Okay. Woohoo. Okay. So far, so good. So this is because they're eigenvectors. So now at this stage, I'm going to do something a little bit magical or clever, maybe. So I'm going to come back to this line here, and I'm going to multiply this line by a negative lambda VP plus 1. So I'm going to take this line right here. So when I multiply both sides by lambda P plus 1, I end up with lambda p plus 1. And specifically, notice it's a negative. So negative lambda p plus 1 times v p plus 1 equals negative, I guess I could write it as C1 lambda p plus 1 V1 minus dot 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 minus CP lambda p plus 1 VP. Okay. So notice, this is a little bit strange, but notice we have a lambda p plus 1 times v p plus 1, and we have a minus of the same thing. The only difference being the top one is plus and the bottom one is minus. Okay. And so we can add those two lines together. So positive lambda p plus 1 v p plus 1 minus lambda p plus 1 v p plus 1 is 0. And then we could combine all of our v1s and all the way to vp's. So I have something times C1 V1 plus dot 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 plus something times CP VP. And this something is going to be this stuff. Okay. So we're going to have lambda 1 minus, oops, I lost my 1, lambda p plus 1. And we're going to have lambda p minus lambda p plus 1. Okay. So what can you tell me about the vectors v1 to vp? How do we define them? So these vectors from Ben and from Evan, these vectors are linearly independent. Okay. And what can you tell me about the C's? Yeah. Some of them could be 0, but they're not all 0, like Dibbs and Gerald said. So they're not all 0. Okay. So we have right here, a linear combination of vectors that adds to 0. And since we have a linear combination of vectors that adds to 0, and we have linearly independent vectors, the only way that could happen is if we have the trivial solution. Well, we know we're not getting the trivial solution from our C's, right? So if we aren't getting our the trivial solution from our C's, then we must be getting this trivial solution from our lambdas. Okay. Which is to say, notice what this would be saying. And this would be true for at least one of these. Yeah. So at least one of these must be true. So this is, so if, for example, that was lambda 1, that would be telling us that lambda 1 equals lambda p plus 1. So the lambdas are not distinct. So that's a contradiction. Yay. So we assumed that they were we suppose that they were distinct. So it's contradiction. Therefore, V1 to VR are linearly independent. Something like that. Tibbs, what would give you that feeling? I won't deny that I looked at this in prep for class yesterday and was like, huh, that'd be a good question for the assessment. So your hunch is at least reasonable. All right. You might say, why is this going to matter? This is going to be helpful to you because it may save you a little bit or be a check later on. Mostly it's a cool proof. But basically the value to this is if you have a n by n and you have n distinct eigenvalues, then you know that the eigenvectors will be linearly independent. And n yesterday we introduced this idea of geometric multiplicity. You may or may not remember that, but if you do remember it, this would be like saying that the geometric multiplicity of every eigenspace is just 1.